So hello everyone, thank you for attending our today's super spreader seminar series. So this is our third talk. First, I would make our line acknowledgement. So we acknowledge the lines of OMNI-RÉUNIS network's head office is located on York University. Recognize that many indigenous nations have long-standing relationships with the territories upon which York University campus are located that precede the establishment of York University. York University acknowledges its presence on the traditional territory of many indigenous nations. The area known as Toronto has been caretaken by the Anishinaabeg Nation, the Haudenosaunee Confederacy, and the Huron-Wendat. It is now home to many First Nation, Inuit, and Métis communities. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. This territory is subject to the Dish with One Spoon, Wampum Belt Covenant, an agreement to peacefully share and care for the Great Lakes region. So I just want to make more strengthen the introduction of our super spreader seminar. So this is a bi-weekly seminar, and it is a platform to spread scientific knowledge about the One Health research framework and showcase the research progress of the over 30 OMNI-RÉUNIS HQPs within the networks. So today, our speaker is Juping Ji, and she is a postdoctoral researcher with Dr. Hao Wang at the University of Alberta. She was awarded her PhD degree in applied mathematics from University of New Brunswick in 2021, and she is working on modeling MPIs to evaluate the past policy strategies for the effectiveness. So her research interests are in differential equations and applied dynamic systems with applications in biology and ecology. And she is interested in mathematical modeling of infectious disease, intribute predation model, and the stoichiometric modeling. And today, she will present the talk about success or failure of non-pharmaceutical interventions on infectious disease mitigation, modeling the impact of atmospheric conditions. So over to you. I will stop sharing. Dr. Juping.
Yeah, I show my screen. Could you see my screen?
Yeah, perfect.
Yeah. Thanks for inviting and giving me this opportunity to present our joint work. It is a joint work with Judy Kong, Priya Hao Ning, and James Watmore. This talk is divided into the following 7 parts. Firstly, I will give a brief introduction. Since the identification of coronavirus in December 2019, we all know that COVID-19 virus has been sweeping the globe. Like many other viruses, coronavirus doesn't survive on non-uncertain surfaces and in the air when exposed to a high amount of ultraviolet light, warm and humid conditions. The lab results reported by Washington Post in 2020 shows that increases in temperature, humidity, and sunlight can all speed up how fast the virus is destroyed. Based on the measurement of half-life of virus, when exposed to these three elements, as shown in Figure 1, on the environmental surface, where the temperature is room temperature 70 to 75 degrees, the humidity increases from 20% to 80%. In the absence of sunlight, the half-life of virus decreases from 18 hours to 6 hours. If we fix the humidity 80%, the temperature increases from 70 to 75 degrees to 95. Still in absence of sunlight, the half-life of virus decreases from 6 hours to 1 hour. Fix the temperature 70 to 75 degrees, the humidity is 8%. Adding the sunlight, the half-life of virus decreased from 6 hours to 2 minutes. These lab results indicates that environmental conditions can affect the survival of virus. In 2020 and 2021, many existing results also show that the environmental conditions can affect the virus survival. In 2020, Bucher pointed out that the virus survival is enhanced by low air temperature and relative humidity. The stability of coronavirus can be affected by the environmental conditions. In their work, they find that the virus is more stable at low air temperature and low humidity. The transmission of COVID-19 can also be affected by weather and climate significantly. And there are also evidence shows that the environmental surfaces can be conducive to the spreading of the virus. We know mathematical modeling is a power tool for us to better understand the transmission dynamics of a disease. So in our work, we want to construct a disease transmission model. Existing results show that environmental conditions can affect the survival of the virus. So in our work, we intended to explore the effect of temperature, humidity on survival of the virus. The COVID-19 virus can persist outside the host, so it is necessary to explore the dynamics of the virus on the environmental surface. The COVID-19 is mainly spread through droplets. The droplets are usually produced by cough, talking, and sneezing of infected individuals, and then transmit to uninfected individuals by direct inhalation or contamination of nearby surface. So in our work, the transmission will be divided into two parts: direct transmission and indirect transmission. Since 2020, more and more people have get vaccinated. So in our work, we also take the vaccination compartment into our consideration. In our work, the total population will be divided into the following 7 parts: susceptible individuals, exposed individuals, infected individuals with symptom or a symptom, the recovered individuals, and the vaccinated individuals. The population flow among those compartments is given in figure 2. The susceptible individuals enter the incubation period when they are infected with virus. Upon the incubation period ends, the exposed individuals enter either asymptomatic infected individuals or symptomatic infected individuals, depending on whether symptoms occur or not. It will take times of symptomatic infected individuals and asymptomatic infected individuals to recover. And the recovered individuals and vaccinated individuals may lose immunity and infected again. Here, the capital P is the virus on the environment. They are shielding from the infected individuals. C is the shielding rate. Here, mu denotes the death rate of infected individuals due to the disease. Here, D denotes the death rate of virus on the environment. Alpha of the function alpha of P denotes the indirect incidence. Both of these interactions among compartments, we propose a SEIAR model with vaccination compartment and indirect incidence. Compared with the symptomatic infected individuals, exposed individuals and asymptomatic infected individuals can spread virus at reduced possibility. So we assume the transmissibility of exposed, relative transmissibility of exposed individuals and asymptomatic infected individuals are theta E and theta I, respectively. The existing results show that the environmental conditions can affect the survival of virus. So here we assume the death rate of virus is a function which depends on the temperature and the humidity. Here, the indirect part of the incidence term alpha of P is defined by a point-2 function. The description of our parameters is described in table 1. Compared with the total population N, the virus induced death is negligible. So here we assume mu equals 0. Then the derivative of total population with respect to time t equals 0. So we can get the total population is a constant in our model. And for our system, we can obtain that the system is well posed. That is for any non-negative initial condition. Our system always admits a unique solution, which remains non-negative and bounded for all non-negative time. We also find our system has a disease-free equilibrium E0. Is given by this one. It is well known that basic reproduction number is an important index to measure the disease transmission potential. So here we calculate the basic reproduction number R0 of our model. From this expression of R0, we can observe that the basic reproduction number can break down to two components. secondary infections generated from the infected individuals and from the virus on the environment. Taking R naught as the threshold index, we can obtain the local stability of disease-free equilibrium. We proved if R naught less than 1, E naught is locally asymptotically stable. If R naught is greater than 1, the E naught is unstable. In our model, there are more than 10 parameters. So each variation of each parameters may affect the trend of epidemic. Sensitive index helps us determine the relative change in a state variable. So we calculate the sensitive index of the R naught to the following parameters. Here, the sensitive index is normalized. From table 2, we can see that the direct transmission rate beta has a strongest effect on the R naught. Increasing the transmission rate beta, the value of R naught will increase. It may contribute to the transmission of the disease. The sensitive index of R naught of D is negative. The negative relationship indicates that increasing the death rate of virus, it will decrease the value of R naught, which may mitigate the transmission of epidemic. Environmental conditions can affect the death rate of virus. So we consider the death rate as a function of temperature and humidity. In 2020, Bill curve pointed out that the half-life of virus is determined by a function of temperature and humidity. The half-life of virus can be obtained at any combination of temperature and humidity. E2 minus dt is the surviving probability of virus at time t. Here is half-life of virus, so E2 minus dt equals 0.5. With this relation, we can calculate the death rate of virus equals 92 over t sub 1 over 2. Now, to explore the effect of temperature and humidity on the death rate, we collect climate data of 2 cities, Edmonton and Vancouver. We collect the temperature and humidity data from January 1st to December 31st in 2021. Figure 8 describes the average temperature of 2 cities, and figure B describes the average relative humidity of 2 cities. From figure 8, we can see when in cold months, the temperature of Vancouver is obviously higher than that in Edmonton. And in warm months, the 2 cities have a close temperature. And in figure B, we observed that the humidity of Vancouver is higher than that in Edmonton. With the function of D of T and H, we substitute the temperature and humidity data of Edmonton and Vancouver into the function D. and obtained the death rate of virus in 2 cities respectively. As shown in Figure A, the death rate of the virus on surface in Vancouver is higher than in Edmonton. That's because the Vancouver has higher temperature and higher humidity. To better understand the effect of humidity temperature on R0, we plot the relationship between climate data and R0. From Figure B, we can see that at low temperature and a low relative humidity, the basic reproduction number R0 is greater than 1. It indicates that the low air temperature and low humidity contribute to the transmission of virus. For higher temperature and higher relative humidity, the value of R0 decrease less than 1. That means the higher temperature and humidity may indicate the transmission of virus. The sensitive index shows that beta has a strong effect on the value of R0. Here we consider time-dependent transmission rate beta. Involves method is a useful tool to obtain the transmission rate. In 2012, in this paper, they extract the transmission rate by involves method use confirmed data. In our work, we also want to use involves method to obtain the transmission data with using the daily confirmed cases. We let this denote the values of variables on ice day. Given the initial value of all variables, we can obtain SI, EI, II, and PI. Then substitute these values on ice day. We can obtain into here. We can obtain the time series transmission rate beta. To obtain the transmission rate beta of 2 cities, Edmonton and Vancouver, we collected the daily confirmed cases of these 2 cities from January 1st to December 31st in 2021. Since the number of daily confirmed cases may be underreported or delayed during weekend, so we take a 7-day averaged cases to reduce the inaccuracy of the reported confirmed cases. We plot the daily confirmed cases of 2 cities in Figure A. From Figure A, we can see in June and July, the confirmed cases is lower than in other months. And after April, the daily confirmed case of Vancouver is higher than the daily confirmed case of Edmonton is higher than Vancouver. Then we use the involves method and using a daily confirmed case to extract the transmission rate of 2 cities, which it is presented in Figure B. Compared with the June and July, the transmission rate in November and December is higher than the June and July warm months. In this figure, we plot the transmission rate of Edmonton obtained by the inverse method in figure A. Then we substitute the transmission rate obtained by the inverse method to our model and evaluate the confirmed cases. Then compare the confirmed cases with the notification data. We can find the inverse method can show a perfect fitting with the notification data. Here the red curve is a fitting curve. We also compared the confirmed cases by inverse method with the notification data of Vancouver. We also find the transmission rate of Vancouver obtained by the inverse method can show a perfect fitting with notification data. In this part, we will use machine learning and make some predictions. In our work, we employ GBM to estimate the transmission rate from the average temperature and humidity. In our work, we use a GBM package predict function in R. We divided our dataset into two parts, a training dataset and a testing dataset. The training dataset is used to calibrate the parameters. The testing dataset is used to test model performance in making predictions. We use mean absolute percentage error and mean absolute error to estimate the differences between collected data and predicted data. These are the formulas of MAPE and MAE. Here, Xi denotes the ith component of the vector of actual values. Yi is the ith component of the vector of prediction values. The training data set is composed by climate data and transmission rate beta t obtained by inverse method. We train GBM for different training duration, increasing from 233 days to 323 days by 1 week, 4 days, and training GBM to test 4 weeks, 28 days to make prediction. Based on the climate data on test duration, we will use GBM to make predictions of transmission rate beta t. Then we are compared the value of confirmed cases and notification data. As shown in table 5, we can observe that when we choose training days for 281 and 295, 302 days, small MAPEs and small MAEs are obtained. Then in the following, we present our prediction results in following figures. Firstly, we training 281 days from January 1st to October 50th. here we just use climate data of Vancouver. The red curve, we can see the red curve fit perfectly with the notification data, and the yellow prediction curve show a good fitting with the local minimum point. In this figure, we training 295 days and test 28 days. It also shows a good fitting with notification data. Finally, we training 302 days from January 1st to October 29, and then test 28 days following from the training duration, and we can also obtain a good fitting. In this talk, we proposed an SEIR model with vaccination, compartment, and indirect incidence. Since the environmental conditions have a great effect on virus survival, so we focus on the effect of humidity and the temperature on COVID-19 transmission. In our work, we use inverse method to evaluate the time-dependent transmission rate, and finally we'll use a GBM to estimate the transmission rate from the average temperature and relative humidity, and make some predictions. And we can our model can be used to make predictions in a short time. Thanks for your attention.
Thanks, Dr. Juping. So very interesting talk. Do we have any questions or comments? So I guess Dr. Juping has already explained the materials very well. But I do have a question about for the, I remember you present R0 plot for the temperature and the humidity for that one.
Yeah.
So I'm just curious about how to incorporate for the temperature and the humidity into your R0.
Because the expression of R0 here we have D. Here D is depend on temperature and humidity. So we substitute the daily temperature and humidity data into the R0.
So you mean like for the temperature and the humidity will affect for the daily death rate?
Yeah, you use this expression, then use this function, we can obtain the D, then substitute D into R0, then we can get the effect of environment conditions on R0.
Okay, I got it. Thank you. So I do have other questions, but I can leave it later. So I see Professor Juping Ji has questions. So please go ahead.
Thank you. In fact, thank you for this interesting presentation. I see you incorporate many factors, but more importantly, you are, as Paige just mentioned, you are considering basically the weather or the season or the temperature. So for in your model, like of course, like it is reflected in the parameter D.
Yeah.
So this is like here. for the data you use, also the simulations you do you think this is related to the different strain of virus, or this dependency on temperature and H? So it's like universally similar or the same to all the different strains. For example, from the beginning you have Alpha, Delta, now you have Omicron. So have you?
Here we didn't consider different viruses.
Basically, you are assuming for SARS-CoV-2, for this kind of family of virus, the evolving or mutation of the virus with different strains, they have the similar response to the temperature and to the temperature.
Yeah, that's a good point, but here we didn't consider.
Because this is research is related to early warning.
Yeah.
So as you can see, because this is important.
Yeah.
Like for example, just like flu, if you see the weather is getting cold, the temperature drops. And then this research will help to develop the early warning indices to tell people you will see high peak of outbreaks.
Yeah. We will consider in the future. That's a good suggestion.
Thank you. In fact, that is my question, because this is like now people started to look at how especially the weather and the season about the transmission of the virus. Yeah, thank you.
Thank you. And there is the message in chat. And our paper didn't publish, so we didn't have link.
Okay. So actually, I have a following question. Like Professor already mentioned that for the effects of different variants, because I think this is a very significant factor will affect for the transmission. So, and it also maybe can affected by the weather and for the temperature and other factors. And another question is about why do you choose for the death rate to incorporate for the temperature and humidity effects? Because maybe for the transmission rate, like for the beta, it's more, it will be also affected by the weather, right? Like during the particular season, people may be more easily to, like, I'm not sure about that, but
our work more just modeling the effect of weather conditions. So, but for the simulations, we can just show the effect to show the effect not very clearly. Just to say that the high temperature and high humidity may reduce the value of or not.
So, like, because in your second one, like using the gradient boosting machine method, using that one, you're showing like for the beta will be affected by the weather, right?
Yeah. In the machine learning part, we use weather condition, but we cannot find a clear relationship between the climate data with the transmission rate at the moment.
Okay, so didn't find any like was a clear relationship about that.
Yeah.
Okay, thank you for your
Thank you.
explanation. But I see there is another question in the chat.
I have this paper is in preparation, then submit.
Okay, thank you. And I do have another question. Sorry, I have two questions. So this a very interesting talk and very interesting work. Another question is about like in your sensitivity analysis, you're showing that for the death rate, it is not sensitivity to the R naught, right?
Yeah.
But you incorporate for the temperature and that's into that one. So can we like, because in this way, maybe for the weather effect will be not like, visible in your R naught contour plot.
Maybe I didn't choose suitable parameter values. Here it shows D is less affect the R naught.
Okay, so I mean, like in this way, you consider like because the death rate is not sensitivity to the R naught.
Yeah.
So
it's
if you're
less sensitive.
temperature,
less sensitive.
Yeah. Because the sensitivity, the value is like near to the zero. It is negative 0.014. It is very low, right?
Yeah.
It is
so that's
why
here the sensitive index is normalized.
Yes.
Yeah.
So 0.01 is like very low level.
Yeah.
I know,
so maybe I will choose other parameter values to show the sensitivity index.
Okay. So I
yes, thank you.
Why this one is not sensitive, but in your R naught contour plot, it shows like if you have like higher temperature, the R naught will be less.
Yeah.
Because that rate is not sensitive to the R naught. Okay, just curious about that.
Thank you. That's a good question.
Did you have another comment? Because I see you raise your hand. Professor Juping Ji, do you have other questions?
Yeah. In fact, like I see Professor Asifa having a question asking for preprint because you are working on this paper. I do have maybe some suggestion.
Yeah.
Now, based on your presentation and the questions. First, indeed, the by what we know from the data, the impact of temperature, especially the season, indeed are important, but it works differently, for different virus, different strain of the virus. Of course, like because you put it to the impact of death rate. Currently the death rate due to infection are becoming smaller and smaller. Comparing to, you see, the other factors. Also, people treated this now in North America, treated as a flu, a big flu. So this is the reason, because they do have similarity in terms of symptoms as flu. So I would suggest when you consider this impact, you may separate before Omicron and after Omicron. The major differences is the death rate. there's a, obviously there's a big difference in terms of death rate. So this is the one. If you separate, become maybe two projects. One is working for the virus before Omicron, and then starting for Omicron, where you consider the impact of temperature. There's a even interesting problem like nowadays, especially currently, the flu is going on. It's the flu season, and then the impact of the Omicron, the transmission of Omicron is similar to the flu.
Yeah.
And then in the season, basically you want to treat, you have Omicron. But anyway, it's a suggestion. Professor Wang, because like your supervisor, your group will have a discussion, because it will be interesting to see the flu and the Omicron work together to to spread, how to improve how to understand the transmission. So in this case, you may not want to put the temperature to the death rate, as Pei mentioned. So the seasonal effect to flu is mainly on the transmission contact part. The instance, you may want to put the temperature to the beta, the instance term. So that could be more interesting. Anyway, that is my personal opinion.
There will be more interesting. Yeah.
Thank you. Very interesting talk.
Juping, yeah. Thanks, Huaiping.
Yeah.
Juping, I remember that was suggested, right? The transmission depending on temperature and humidity. That was suggested a long time ago, right?
Yeah, that part could be more heavier. The impact could be, because nowadays people consider the death rate only below 0.1, 1% below 1%. So if you add the temperature to that, it's minor.
Yeah, I think we can consider that. And yeah, Huaiping, we are also a PhD student is working on the mutation stuff, but we haven't incorporated the temperature stuff into the mutation. So I think this project, Juping is working on before Omicron. So data, I think she used just before Omicron. So after Omicron, it's a completely different story.
Yeah. So that's why, you stop cut off before Omicron, and then this, otherwise the reviewer will ask you, this would be a problem.
Yeah, so Juping, a few things. We should look at Omicron case, of course, this year's data, can look at that, and also consider how the transmissibility depending on the weather conditions. That's the second thing, And the third thing is to consider the mutation. I can send you the draft on the mutation stuff. Of course, that one we haven't included the weather conditions, but you can consider adding weather conditions into the mutation model.
Okay.
So we worked out how the mutation occurs depending on the kind of pandemic situation. So the model very complicated. It's kind of you need the evolution of the virus and coupled with the epidemiological models.
Yeah,
that is you are using partially the in-host dynamics.
Yeah, it's kind of a 3-level model. One is the in-host, one is the between host, one is the mutation virus. It's a kind of 3-level model.
Yeah, of course, when you consider mutation, the weather is second layer or low layer of factors to decide the mutation. Mutation is supposed to be the properties of the virus itself.
Yeah, that's why we didn't consider weather into that.
Yeah.
We try to keep track of the probability of mutation, how that depending on the pandemic situation. Because we observe that if the pandemic is more severe, very likely to cause the mutation because it has higher chance. We try to keep track of that probability depending on the pandemic situation. So that's the coupling.
Yeah, that is the interesting part of the virus, because the transmissibility.
Yeah, so that one has been done actually. Juping was not involved. I can show you the draft.
Okay.
Thanks everyone. So do you have other comments or questions? So if not, let's thank our presenter, Dr. Juping Ji again, and thanks everyone for joining us. So see you next week. Thank you.
Okay, bye.
Bye.
Thank you. Bye.
Wow, Professor Wang Ling, huh? Hiding.